Hello, friend. Welcome to a quiet place where the night stretches long and questions drift softer than answers. Tonight we're going somewhere most minds rarely wander before sleep, to the very edge of everything. Not the edge of a cliff, or a shore, or even a world. The edge of existence itself. What lies there? A wall, a door, or perhaps nothing at all. Some say the question has no answer. Others say it has too many. But here in the stillness, we'll let the universe whisper its secrets one breath at a time. Before we begin our gentle drift into the cosmos, if you find comfort in these quiet journeys through space and time, you might like to stay a while. You can softly tap the like button if this feels like home. Subscribe if you would like more stories told in whispers. And ring the little bell not for noise, but so the next quiet night can find you again whenever you need it. Now, let's drift. Tonight we'll float toward the most ancient question humanity has ever asked. It's a question that kept Greek philosophers awake, that haunted medieval monks in candlelit towers, that still puzzles physicists in laboratories humming with machines. If you travel far enough in any direction through all the darkness and all the light, where do you arrive? Is there a place where space simply stops? And if it stops, what could possibly lie beyond a place where nothing exists? The universe as we know it is almost unimaginably vast. Light traveling at 186,000 miles every single second would need 93 billion years to cross from one edge of the observable universe to the other. 93 billion years of constant motion, never slowing, never resting. And yet, even that incomprehensible distance might be only a fraction, perhaps an infinitesimal fraction of what truly exists. But here's something curious, something that feels almost like a riddle written into the fabric of reality itself. The universe is only 13.8 billion years old. So, how can we see evidence of things 46.5 billion light years away in every direction? How can the universe be nearly 7 times wider than the time light has had to travel since the beginning of everything? The answer lives in one of the most beautiful and unsettling truths about existence. Space itself is not still. It doesn't sit quietly like a stage waiting for actors. Space is growing, stretching, breathing outward in all directions every moment of every day. And it's been doing this since the very first instance, since that mysterious eruption we call the Big Bang. Though that name makes it sound like an explosion in space when really it was an explosion of space. Scientists suggest that in the first fractions of a second after the universe began, space inflated faster than light itself could travel. Not because anything was moving through space, but because space was creating itself doubling and doubling again, faster than thought. This period, called cosmic inflation, lasted perhaps 1/trillionth of a trillionth of a trillionth of a second. And in that incomprehensibly brief moment, the universe grew from something smaller than an atom to something vastly larger than anything we can see today. It's as if the universe took one sudden breath, and that breath has been slowly exhaling ever since. Now imagine you're standing in a dark room. In your hand, you hold a candle. The light reaches perhaps 10 feet in every direction before the darkness swallows it. But that darkness doesn't mean the room ends 10 feet away. It only means your light cannot reach any farther. The observable universe works this way. We live inside a sphere of light, not a sphere of space, but a sphere of time. We can only see as far as light has had time to travel to reach us since the beginning. This is the first edge we encounter. Not a wall, but a horizon made of time itself. Beyond that horizon, the universe continues. It must, because the light from those regions simply hasn't reached us yet. Right now, at this very moment, there are galaxies so distant that their light is still traveling through the void, and it won't arrive here for another billion years, or 10 billion. Or perhaps never, because of something we'll explore later, something stranger and sadder than you might expect. But let's stay here at this edge for just a moment longer, because there's a common misunderstanding about what this means. Many people imagine the observable universe as a bubble with Earth at its center, as if we occupy some special position in the cosmos. This idea feels ancient, doesn't it? It echoes Ptolemy, who placed Earth at the center of everything with the sun and planets spinning in perfect circles around us. It whispers of a time when we believed we were the reason for all creation. But we are not at the center. There is no center. If you could somehow transport yourself to the most distant galaxy, we can see a galaxy whose light has traveled 13 billion years to reach our telescopes, and you looked back toward where Earth used to be, you would see a new sphere of observable universe around you, a different 93 billion light years, different galaxies, different stars, different corners of space entirely. You would be standing at the center of your own horizon, just as we stand at the center of ours. Every point in the universe is the center of its own observable universe. Every star, every planet, every wandering atom, drifting in intergalactic space looks around and sees itself surrounded by the same sphere of light and time. It's one of the most democratic truths in all of physics. No place is special. No location is more important than any other. We are all equally centered and equally adrift. Research shows that this principle, called the cosmological principle, suggests the universe looks roughly the same in all directions no matter where you stand. Galaxies cluster in similar ways. The cosmic microwave background radiation, a faint glow left over from the universe's infancy, has nearly the same temperature everywhere we look. The laws of physics appear identical billions of light years away, as they do in laboratories here on Earth. This uniformity is both comforting and deeply strange. It means that if you traveled impossibly far in any direction, you wouldn't find an edge marked with a sign saying, "End of universe." You'd find more galaxies, more stars, more space breathing outward. But here's where the mystery deepens, where the question grows softer and harder to hold. If the universe looks the same everywhere, if it continues beyond our horizon in all directions, does it go on forever? Is infinity not just a mathematical concept, but a physical reality? Or is there some subtle curvature, some hidden geometry that eventually bends back on itself, so that if you traveled far enough in a straight line, you'd somehow arrive back where you started, like an ant walking around a sphere, never finding an edge, but never escaping either? Some nights the question feels too large to carry, and maybe that's the point. Maybe the edge of the universe is not something to be found, but something to rest beside, like sitting at the shore of an ocean that has no other side. Throughout history, humans have always sought edges. We mapped coastlines, climbed mountains, drew borders around nations and kingdoms. We wanted to know where things ended, so we could understand where we belonged within them. But the universe offers no such comfort. It stretches away from us in every direction, indifferent to our need for boundaries, unconcerned with our desire to see the frame around the picture. And perhaps that's okay. Perhaps some questions are meant to be lived with, not answered. Some edges are meant to be wondered about in the quiet hours before sleep, when the mind can drift without needing to arrive. You don't need to solve the mystery tonight. You don't need to understand it all. The universe has been expanding for 13.8 billion years. It can wait for you to catch up. Or not. It doesn't mind either way. But there's one more thing worth considering before we move forward. One small, devastating detail. When we look out at distant galaxies, we are not seeing them as they are now. We are seeing them as they were billions of years ago, when the light we're receiving first began its journey, that galaxy glowing in our telescope. It might have faded centuries ago. Its stars collapsed into darkness, its planets gone cold. We are looking at ghosts. We are seeing the past preserved in light, traveling across a universe that has changed entirely in the time it took the light to reach us. Some believe this means we live in a universe made partly of memory. The sky above us is an archive of what once was not, what is. And somewhere impossibly far away, a different sky holds the light from our own sun, from a time before humans existed, before Earth had a name, before anything looked up and wondered why. The edge of the universe, then, is not just a place, it's a moment. It's a boundary between the past we can see and the present we cannot. between what has reached us and what never will. And so, the question changes shape in the darkness. We're no longer asking where the universe ends. We're asking when. We're asking if endings even exist in a place where time and space breathe together, inseparable, eternal. But we've only just begun to drift. There are stranger horizons ahead, older light waiting to be understood, and boundaries that bend in ways that make the mind quiet with wonder. The edge is not one thing. It is many things layered like veils, each one revealing something new when we pull it gently aside. Shall we continue? The universe has been waiting since the beginning of time to show you what comes next. There is a light older than stars, older than galaxies, older than anything that has ever had a name. It fills the entire universe, touching every corner of space, passing through your body, right now, as you listen, as you breathe, as you drift. You cannot see it with your eyes, but it's there humming quietly at a frequency below, read below warmth in the territory of microwaves. Scientists call it the cosmic microwave background, but perhaps we should call it what it truly is, the afterglow of creation itself. This light is a ghost, the remnant of a moment when the universe was so young, so hot, so dense that nothing could exist as it does now. No atoms, no stars, no darkness between things. Just energy pure and blazing, filling everything. And when we look back at this light, we are not simply looking into the past. We are looking at the edge of visibility itself, the wall beyond which no telescope, no instrument, no clever arrangement of mirrors and mathematics can ever see. It is the oldest thing we will ever witness, and it is in a very real sense the first boundary. In 1964, two scientists named Arno Penzias and Robert Wilson were trying to eliminate noise from a radio antenna in New Jersey. They were not searching for the origins of the universe. They were troubleshooting. The antenna kept picking up a persistent hiss, a background static that wouldn't go away no matter how they adjusted their equipment. They cleaned out pigeon droppings. They recalibrated. They pointed the antenna in different directions. The hiss remained uniform, unchanging, coming from everywhere at once. What they had found quite by accident was the echo of the Big Bang, the faint whisper of a universe that had been white-hot 13.8 billion years ago. This discovery would earn them the Nobel Prize, though at the time they didn't fully understand what they were hearing. They thought it might be interference from New York City, or perhaps a flaw in their instrument. It took conversations with theoretical physicists at nearby Princeton to realize the truth. The universe itself was humming, and they had tuned into its oldest song. The cosmic microwave background, or CMB, is light that has been traveling for nearly the entire age of the universe. It was released approximately 380,000 years after the Big Bang during a moment cosmologists call recombination. Before this moment, the universe was too hot for atoms to form. Electrons and protons flew freely through space, constantly colliding, constantly scattering light. The universe was opaque like a thick fog. Photons, particles of light, couldn't travel more than a tiny distance before smashing into something and bouncing in a new direction. But as the universe expanded, it cooled, and eventually it cooled enough for electrons to settle into orbit around protons, forming the first hydrogen atoms. Suddenly, light could travel. For the first time since the beginning, photons were free to move in straight lines across space. The fog cleared, the universe became transparent, and the light from that moment, the moment of first transparency, has been traveling ever since. Research shows that this light was initially released as visible light, glowing orange and red like the surface of a cooling star. But as the universe continued to expand, the wavelengths of this light stretched with it. The light grew longer, redder, cooler. Over billions of years, it shifted from visible light into infrared, and then further still into the microwave range. Now it has a temperature of just 2.7 degrees above absolute zero. It is the coldest light in the universe and also the most evenly distributed. Wherever you point a sensitive radio antenna, there it is whispering the same ancient story. And here's something extraordinary. This light surrounds us in every direction, forming a perfect sphere. But it is not a sphere in space. It is a sphere in time. When we observe the CMB, we are looking backward 13.8 billion years, seeing the universe as it was when light first escaped the primordial fog. We are seeing the baby picture of everything, but we cannot see beyond it. This is the wall, the barrier, not a physical wall made of matter, but a wall made of opacity. Before recombination, before atoms formed, the universe was simply too dense for light to travel. Any photons that might have existed before that moment were scattered, endlessly trapped in the fog, unable to reach us. So, even if we build more powerful telescopes, even if we develop technologies beyond our current imagination, we will never see the universe as it was in its first 380,000 years. That information is hidden behind a veil of light itself. Some scientists suggest this is like standing inside a glowing cloud. You can see the cloud around you luminous and beautiful, but you cannot see through it to what lies beyond. The CMB is our glowing cloud, and we are forever inside it, looking at its inner surface, wondering what came before. This raises a haunting question. If we cannot see past the CMB, how do we know anything about the earlier universe? How do we know about inflation, about the Big Bang, about the first fractions of a second? The answer is mathematics and inference and the faint patterns encoded in the CMB itself. When scientists map the cosmic microwave background in extraordinary detail using satellites like COBE, WMAP, and Planck, they find that it is not perfectly uniform. There are tiny fluctuations in temperature variations of only a few millionths of a degree. These fluctuations are not random. They form patterns, ripples, echoes of sound waves that traveled through the infant universe when it was still a plasma before atoms existed. These ripples tell us about the density of matter in different regions, about the seeds that would eventually grow into galaxies and galaxy clusters, about the geometry of space itself. By studying the size, shape, and distribution of these ripples, physicists can work backward, reconstructing the history of the universe long before the CMB was released. It's like hearing a bell ring and deducing from the tone and the fading echoes what the bell is made of and how it was struck. One of the most profound discoveries encoded in the CMB is the confirmation that the universe is spatially flat. Not flat like a piece of paper, but flat in a geometric sense, meaning that parallel lines will remain parallel forever, that the angles of a triangle add up to exactly 180 degrees, no matter how large the triangle is. This flatness is astonishing because it requires an almost perfect balance between the density of matter and the expansion rate of the universe. If the universe had even slightly more matter, it would curve inward, eventually collapsing back on itself. If it had slightly less, it would curve outward, expanding so fast that galaxies could never form. But it is balanced almost impossibly so. Scientists suggest this precision is a signature of cosmic inflation, that violent burst of expansion in the first instant after the Big Bang. Inflation stretched the universe so rapidly that any initial curvature was smoothed out, like pulling the wrinkles from a bedsheet. What remains is a universe so geometrically flat that it might theoretically extend infinitely in all directions. But let's return to the light itself, because there's something almost poetic in the fact that the oldest light we can see is also the faintest. It's not bright. It doesn't shine in the night sky. You could stare upward for your entire life and never notice it with your naked eyes. And yet, it is everywhere, filling the gaps between stars, passing through walls, through oceans, through mountains. Every cubic centimeter of space contains hundreds of photons from the CMB. You are bathed in them always. In a way, this light is the closest thing we have to a universal constant of memory. It carries information from a time before planets, before stars, before anything solid existed. And unlike human memory, which fades and distorts, the CMB is faithful. It has not forgotten. It still holds the pattern of density fluctuations from 13.8 billion years ago, preserved in the structure of its temperature map. like a photograph that has somehow survived the entire age of the universe. But there's a sadness woven into this too, because the CMB is slowly fading. As the universe continues to expand the wavelengths of this light stretch further and further, the temperature drops. In trillions of years, it will cool to the point where even the most sensitive instruments imaginable could no longer detect it. The afterglow will become indistinguishable from the absolute cold of empty space. Future civilizations, if any exist, will live in a universe without this light. They will have no direct evidence of the Big Bang, no baby picture, no wall of first light to study. They will inherit a cosmos that has forgotten its own beginning, and perhaps they will look up at their night sky darker and lonelier than ours, and wonder if the universe had an origin at all, or if it has simply always been infinite and cold with no story to tell. We are fortunate in a sense to live in this particular epoch, an epoch where the universe is old enough to be interesting, but young enough to still remember, where the evidence of creation is still visible, still measurable, still glowing faintly in every direction. A few billion years from now, the galaxies we see today will have drifted beyond our cosmic horizon. The CMB will have cooled beyond detection. The universe will offer fewer and fewer clues about its past. We live in the age of answers. Future ages may live only with questions. Have you ever wondered what it would feel like to touch this light? Of course you already are. Every moment these ancient photons are passing through you. But you don't feel them because they carry so little energy. They are tired, these photons. They have been traveling for almost 14 billion years, and the journey has drained them. They arrive here not as a blaze, but as a whisper. And yet in their quietness, they are the loudest testament to existence itself. They say there was a beginning. There was a moment when nothing became something, when silence became light, when emptiness became everything. The CMB is not the edge of the universe in space, but it is the edge in time. It is the furthest moment we can see, the oldest message we can receive. Beyond it lies the unknowable, the dark age before light could travel the mysteries that no observation can ever resolve. It is a boundary drawn not by walls or distance, but by the fundamental nature of information and visibility. And so we stand here in the present, surrounded by the past, looking at a wall made of light, knowing that behind it, hidden forever, is the true beginning. Not the beginning we can see, but the beginning we can only imagine. The first instant, the first breath, the moment when time itself began to flow. But if the CMB is the oldest light we can see, it is not the only boundary we will encounter. There are other edges stranger and more subtle waiting further along this journey. Horizons that move, regions of space we will never reach no matter how long we travel. And perhaps most haunting of all galaxies that are slipping away from us, not because they are moving, but because the space between us is growing faster than light can cross it. The universe, it seems, is full of goodbyes. Let's drift toward them together and see what they have to teach us. Imagine standing in the center of a perfect sphere. In every direction you look, the distance to the edge is exactly the same, 46.5 billion light years. North, south, east, west, up, down, all precisely equal. You are surrounded perfectly centered in a bubble of visibility. And here's the strange part. Everyone else in the universe stands at the center of their own identical sphere. Every star, every galaxy, every wandering speck of dust sees itself as the absolute middle of everything. The universe has granted everyone the illusion of centrality. Or perhaps it's not an illusion at all. Perhaps center and edge are just words we invented to make sense of something that has neither. The observable universe is not the universe. It is simply the portion we can see, the region from which light has had enough time to reach us since the beginning. And this sphere, this bubble of visibility, is both our home and our prison. We can look out, but we cannot step beyond. We can calculate what lies past the horizon, but we can never visit it. We are sailors on an infinite ocean, forever limited to the patch of water illuminated by our single lantern. In 1610, Galileo Galilei pointed a primitive telescope at the night sky and saw something that shattered centuries of belief. Jupiter had moons, 4 of them orbiting the planet like a miniature solar system. This was impossible according to the cosmology of the time. If everything in the heavens revolved around Earth, how could these moons revolve around Jupiter? The observation was simple, almost mundane, but its implications were devastating. Earth was not the center. We were not special. We were simply one world among many, spinning in the darkness. Nearly 300 years later, in 1924, Edwin Hubble made an equally revolutionary discovery. He was studying a fuzzy patch of light called the Andromeda Nebula, using the largest telescope in the world, at the time the Hooker telescope at Mount Wilson Observatory in California. Astronomers had debated for decades whether these nebulae were clouds of gas within our own Milky Way galaxy, or whether they were separate galaxies entirely impossibly distant and unimaginably large. Hubble found a type of star called a Cepheid variable within Andromeda. These stars pulse with a regular rhythm, brightening and dimming in a predictable pattern. And crucially, the period of their pulsation is directly related to their intrinsic brightness. By measuring how bright the star appeared from Earth and comparing it to how bright it should be, Hubble could calculate its distance. The result was staggering. Andromeda was not within the Milky Way. It was nearly 1,000,000 light-years away, a distance so vast it meant Andromeda had to be an entirely separate galaxy, comparable in size to our own. Overnight, the universe grew 1,000,000 times larger, and then it kept growing, because if Andromeda was a separate galaxy, then so were the thousands of other nebulae scattered across the sky. The universe was not one island of stars, it was an archipelago, an ocean of galaxies each containing hundreds of billions of stars, stretching away into distances that made the mind falter. But Hubble didn't stop there. By 1929, he had made another discovery, one that would eventually lead to our modern understanding of cosmic horizons. He noticed that nearly all galaxies were moving away from us, and not just drifting slowly, they were receding at tremendous speeds. More puzzling still, the farther away a galaxy was, the faster it seemed to be moving. This relationship was precise, mathematical, undeniable. Distance and velocity were linked by a constant ratio, now called the Hubble constant. At first, this seemed to suggest we were at the center of an explosion, with everything fleeing from us in all directions. But that interpretation violated the cosmological principle, the idea that no location in the universe is special. The real explanation was far stranger. Space itself was expanding. Galaxies weren't moving through space. Space was carrying them apart, like dots painted on the surface of an inflating balloon. No matter which dot you stood on, all the other dots would appear to be moving away from you. Everyone would see themselves at the center of the expansion. This is why the observable universe is a sphere centered on Earth, even though Earth is not the center of anything. The sphere is not a physical structure. It is a horizon of light, a boundary defined by time and the speed of light. We can see only as far as light has had time to travel since the Big Bang. Beyond that distance, light simply hasn't reached us yet. It's still on its way crossing the void at 186,000 miles per second. But the journey is so long that it won't arrive for billions more years. Or, perhaps as we'll soon discover, it will never arrive at all. Now, here's where the numbers become difficult to hold in your mind. The universe is 13.8 billion years old, so you might reasonably assume we can see 13.8 billion light-years in every direction. But this is one of the most common misunderstandings about cosmology, because while light has been traveling for 13.8 billion years, the space it traveled through has been expanding the entire time. A photon that left a distant galaxy 13 billion years ago has been moving toward us all this time, but the galaxy itself has been carried away by the expansion of space. By the time the photon reaches us, the galaxy is now much farther away than it was when the photon started its journey. Scientists suggest that when we account for this expansion, the most distant objects we can currently observe are now about 46.5 billion light years away. This means the observable universe has a diameter of roughly 93 billion light years. Not because anything travels faster than light, but because the space between us and those distant objects has been stretching the entire time. It's as if you mailed a letter to a friend, and while the letter was in transit, your friend moved to a house farther away. The letter still arrives, but by the time it does, your friend is no longer where they were when you sent it. The universe works this way with light. We see distant galaxies as they were billions of years ago, but those galaxies are now much farther away than they were when the light we're seeing was emitted. And here's something most people never realize. When you look up at the night sky, you are not seeing a single moment in time. You are seeing a timeline. The moon's light takes about 1 second to reach your eyes, so you see the moon as it was 1 second ago. The sun's light takes 8 minutes, so you see the sun as it was 8 minutes ago. The nearest star system, Alpha Centauri, is over 4 light years away, so you see it as it was 4 years in the past. The Andromeda Galaxy appears as it was 2.5 million years ago, and the most distant galaxies visible to our telescopes appear as they were more than 13 billion years ago when the universe was still in its infancy. You are looking backward through time. The night sky is an archive. Every star is a timestamp, a frozen moment from the past delivered to your eyes in the form of light that has been traveling across the void for longer than human civilization has existed. But let's return to the sphere. The observable universe, this 93 billion light-year bubble centered on Earth. One of the most profound implications of this structure is that it means there are regions of space that we will never be able to see, no matter how long we wait or how powerful our telescopes become. Not because they don't exist, but because the light from those regions will never reach us. Research shows that due to the accelerating expansion of the universe, there is a limit to what we can ever observe. Galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they are moving through space faster than light, nothing can do that, but because the space between us and them is expanding so rapidly that even light traveling at its maximum speed cannot close the gap. These galaxies are beyond our cosmic horizon. Their light is perpetually trying to reach us, but the finish line keeps moving farther away. It's like running on a treadmill that accelerates faster than you can run. No matter how much effort you exert, you will never reach the front of the treadmill. You are running forward, but you're also moving backward relative to your goal. The light from these distant galaxies is doing the same thing. It is racing toward us, but the expansion of space is winning. This means the observable universe is not growing. It is in a very real sense shrinking. More and more galaxies are crossing the cosmic horizon every moment, slipping beyond the point where their light can ever reach us. They are not disappearing. They are simply becoming invisible forever. And as the universe continues to expand and accelerate, fewer and fewer galaxies remain within our sphere of visibility. Imagine living in a house where the walls slowly move inward. Each day, one more room becomes inaccessible. One more doorway closes. You are not being crushed. You still have space to move, but the world you can explore is becoming smaller and smaller. In trillions of years, civilizations that arise in the far future will look up at the night sky and see almost nothing, a handful of nearby galaxies. Maybe not even that. The universe will appear empty, lonely, dark, and they will have no evidence that billions of other galaxies ever existed. We live in a unique epoch, an age where the universe is still full of light, still full of visible galaxies, still offering clues about its past. We are cosmologically fortunate. We were born early enough to see the universe while it still remembers itself. But there's another layer to this, another misunderstanding that hides in plain sight. Many people assume that the edge of the observable universe is a fixed shell, a hard boundary that never changes. But it's not. The observable universe is constantly shifting. Every second light from slightly more distant regions crosses the threshold and becomes visible for the first time. The sphere is expanding, but not because the universe is growing. It's expanding because more time has passed, and light from farther away has finally had enough time to reach us. In 1 year, the observable universe grows by about 1 light-year in radius, not because space has expanded by that amount, but because light has had 1 more year to travel. So, in a strange sense, the universe is revealing itself to us slowly, 1 light-year at a time, like a photograph developing in a dark room. But this process has a limit. Because of the accelerating expansion, there will come a point where the rate at which galaxies cross out of our observable universe exceeds the rate at which new regions become visible. The balance will tip. And eventually, the observable universe will begin to shrink in terms of the number of galaxies it contains. Some believe this is one of the universe's quiet tragedies. We are living in the golden age of cosmology. Future generations will have less to study, less to discover, less to see. They will inherit a sky that has gone dark, and they may never know how bright it once was. Do you ever feel small when you think about these distances? 93 billion light-years, numbers so large they lose meaning slipping through the mind like water through open fingers. But maybe smallness is not the right word. Maybe what we feel is something closer to perspective, a recalibration, a quiet understanding that we are part of something older and larger and stranger than we were taught to imagine. And yet, here's the paradox. Even though the observable universe is unimaginably vast, it might be only an infinitesimal fraction of what exists. The universe beyond our horizon could be 1,000 times larger, 1,000,000 times, or truly infinite, extending forever in all directions filled with galaxies. We will never see stars that will never know we exist, worlds where beings look up at their own night sky and wonder if they are alone. Every point in space has its own observable universe, its own sphere of visibility. And those spheres overlap, but they are not identical. If you could somehow travel to a galaxy 10 billion light-years away and look around, you would see a completely different set of galaxies. Some of the ones visible from Earth would have vanished beyond your new horizon. Others invisible from Earth would now fill your sky. You would stand at the center of a new sphere, looking out at a new collection of ancient light. This means the universe is not one story, but countless overlapping stories. Each location has its own past light cone, its own history written in the stars it can see. And none of these stories is more true than any other. They are all equally valid, all equally centered, all equally adrift in the expanding dark. Perhaps this is the deepest lesson of the observable universe. That centrality is everywhere, and therefore nowhere. That every point of view is simultaneously unique and indistinguishable. That the cosmos offers everyone the same gift to horizon, to wonder about a sphere to call home, and an infinite mystery just beyond reach. But the horizon is not the only edge we must navigate. There are boundaries stranger still woven into the very fabric of expanding space, waiting quietly in the mathematics of motion and distance. And one of them holds a question that aches with permanence: what happens to the places light can never reach? There are places in the universe that exist fully and completely, but will never appear in any photograph. Galaxies spinning, with billions of stars, planets circling distant suns, perhaps even minds looking up at their own night skies, wondering what lies beyond. They are real. They are out there. But no telescope will ever find them. No signal will ever reach us from their worlds. Not because they are hidden behind something, but because the space between us is growing faster than light can cross it. They exist in a region cosmologists call beyond the horizon. And the cruel mathematics of expansion means they are lost to us forever. This is not the edge of the universe. It is the edge of connection, the boundary between what we can ever know and what will always remain unknown. And unlike the cosmic microwave background, which is a barrier we might one day understand more deeply, this horizon is absolute, final, unbridgeable. In the early 20th century, a Russian mathematician named Alexander Friedman became fascinated with Einstein's newly published equations of general relativity. Einstein himself believed the universe was static, eternal, and unchanging. To make his equations support this view, he added a term he called the cosmological constant, a kind of anti-gravity that would hold the universe in perfect balance, preventing it from either expanding or collapsing. But Friedman noticed something Einstein had missed. The equations didn't require a static universe. In fact, they seemed to prefer a dynamic one. When Friedman solved Einstein's equations without the cosmological constant, he found three possible outcomes. The universe could be expanding, it could be contracting, or it could be delicately balanced between the two, but it could not be still. Einstein initially dismissed Friedman's work as a mathematical curiosity with no connection to physical reality. But within a few years, Edwin Hubble's observations proved Friedman correct. The universe was expanding, galaxies were moving apart, and Einstein would later call the cosmological constant his greatest blunder. But here's what Friedman's solutions revealed: something far more unsettling than mere expansion. Depending on the density of matter and energy in the universe, space itself could have different geometries. It could be positively curved like the surface of a sphere, where parallel lines eventually converge. It could be negatively curved like a saddle, where parallel lines diverge. Or it could be flat, where parallel lines remain parallel forever. Research shows that measurements of the cosmic microwave background have determined with remarkable precision that our universe is flat or extraordinarily close to it. The density of matter and energy is almost exactly balanced at the critical value needed to keep space geometrically flat. This flatness has profound implications. It suggests that the universe beyond our observable horizon likely extends infinitely in all directions, not just very far, not just unimaginably far, truly infinite. And if the universe is infinite, then the portion we can see, our 93 billion light-year sphere, is not just a small fraction of the whole. It is an infinitesimal fraction, 0%. Because any finite number, no matter how large divided by infinity, equals 0. Let's pause here and sit with that thought for a moment. If the universe is infinite, then everything that can happen has happened. Every possible arrangement of atoms, every variation of structure, every configuration of matter exists somewhere, simply because infinity allows for it. There are galaxies out there identical to the Milky Way. Planets identical to Earth, perhaps even people identical to you, living lives that diverge from yours at some arbitrary moment, making different choices, dreaming different dreams. This idea, called the infinite universe hypothesis, is mathematically consistent but philosophically dizzying. It means that uniqueness is an illusion, that every thought you've ever had has been thought before, infinitely many times, in infinitely many places. And yet, because those places are beyond the cosmic horizon, you will never meet your duplicates. You will never know they exist. They are real but unreachable, present but forever absent from your story. Some scientists suggest this raises a troubling question. If we cannot observe these regions, if we can never receive information from them or send information to them, do they exist in any meaningful sense? This is not a scientific question. It is a philosophical one. Science deals with what can be measured, tested, verified. But the universe beyond our horizon cannot be measured. It can only be inferred. We believe it exists because the mathematics suggests it must. But belief is not the same as proof. And here's where the geometry becomes even stranger. Even if the universe is finite, it might have no edge. This is the possibility of a closed universe, a universe that curves back on itself like the surface of a sphere. Imagine an ant walking on a balloon. The ant can walk forever in a straight line and never reach a boundary, not because the balloon is infinite, but because it loops back on itself. There is no edge to fall off, no wall to encounter. The surface is finite but boundless. A closed universe would work the same way, but in 3 dimensions instead of 2. If you could somehow travel in a perfectly straight line for long enough, you would eventually return to your starting point, approaching from the opposite direction. You could theoretically look through a powerful enough telescope and see the back of your own head billions of years in the past, as the light from your location finally completed a lap around the universe. But current measurements suggest this is not the case. The universe appears to be either flat or very close to flat, which means it is either infinite or unimaginably large, so large that its curvature is undetectable. Either way, the result is the same. There are vast regions of space we will never access, never observe, never confirm. Now, let's talk about what lies in those regions. What could exist beyond the horizon? The cosmological principle assumes that the universe looks roughly the same everywhere, that the laws of physics are consistent, that matter is distributed in similar ways that galaxies cluster and stars form according to the same processes we observe here. This principle is held true for everything we can see. The distant universe, as far as our telescopes can reach, resembles our local universe in structure and behavior, but we have no way to test whether this principle holds beyond the observable universe. It is an assumption, not a fact, and assumptions, no matter how reasonable, can be wrong. It is possible, however unlikely, that the universe beyond our horizon is fundamentally different. Different constants of nature, different forces, different kinds of matter, or perhaps no matter at all. Just empty space stretching endlessly, waiting for something to fill it. There's a thought experiment that physicists sometimes discuss. Imagine you are standing on a beach looking out at the ocean. You can see waves, water, perhaps a distant ship, but you cannot see past the horizon. You cannot see the other side of the ocean. Now, suppose you've only ever stood on this one beach at this one location at this one moment in time. What can you reliably infer about the rest of the ocean? You might assume it's similar, more water, more waves, maybe more ships. But you cannot be certain. Perhaps the ocean ends just beyond your line of sight. Perhaps it transforms into something entirely different, ice or land or something you have no words for. The observable universe is our beach, and we are making reasonable assumptions about what lies beyond. But reasonable is not the same as certain. One of the most disorienting aspects of the cosmic horizon is that it is not a place. It is a relationship between you and the expansion of space. If you could somehow travel to a galaxy currently at the edge of our observable universe, the horizon would move with you. You would find yourself at the center of a new sphere of visibility, looking out at a new collection of galaxies. Some of the ones visible from Earth would now be beyond your horizon. Others previously invisible would now fill your sky. This means the horizon is not absolute. It is relative, personal. Every observer has their own horizon, and no two are exactly the same unless the observers occupy the exact same location. The universe does not have one edge. It has as many edges as there are viewpoints, and every edge is equally valid, equally true. But there is one aspect of this that feels almost tragic, because the horizon is not static and it is not expanding to include more galaxies. It is in a sense contracting. Due to the accelerating expansion of the universe, galaxies that are currently visible are slowly crossing our cosmic horizon, slipping beyond the point where their light can ever reach us again. Every moment, the universe is losing galaxies from our observable sphere. Not because they are moving away, they are not moving at all, but because the space between us and them is growing too quickly. Scientists suggest that in trillions of years, the only galaxies still visible from Earth will be the ones gravitationally bound to us, our local cluster. Everything else will have vanished beyond the horizon. The night sky will be nearly empty, and any civilizations that arise in that distant future will have no evidence that other galaxies ever existed. They will look up and see a handful of stars, and they will believe that's all there is. They will have no cosmic microwave background to study, no distant galaxies to measure, no expansion to observe. They will live in a universe that appears static, small, and lonely. And they will be wrong, but they will have no way to know it. We are living in a cosmologically privileged era. an age where the universe is still young enough to remember its origins, still full enough to reveal its structure. We can see the afterglow of the Big Bang. We can measure the expansion. We can map the distribution of galaxies across billions of light years. Future beings will not have these gifts. They will inherit a universe that has forgotten itself. And perhaps this is the deepest lesson hidden beyond the horizon. That knowledge is not eternal, that there are truths we can access now that will be inaccessible later, that the universe is not just expanding in space, it is also expanding away from the possibility of being understood. Have you ever wondered what it means to exist in a place that no one will ever see? A galaxy beyond the horizon is still real, its stars still burn, its planets still orbit. If there are beings living there, they still think, still feel, still wonder about their place in the cosmos. But they are unreachable, not because they are far away. Distance alone is not the problem. They are unreachable because the very fabric of space-time is pulling them away faster than any signal, any message, any evidence of their existence can ever cross the gap. They are not gone. They are simply elsewhere in a part of the universe that will never intersect with ours. And somewhere perhaps they are looking up at their own night sky, wondering if there are other galaxies beyond their horizon, other minds asking the same questions, other edges they will never cross. The universe is full of rooms we cannot enter, full of stories we cannot read. And the most difficult part is knowing they exist, knowing that absence is not the same as non-existence, that there are truths out there real and complete that we will simply never touch. But even this is not the final boundary, because there is another edge, subtler and stranger, still woven into the mathematics of acceleration and the relentless march of cosmic expansion. It is called the event horizon of the universe, and it marks the line between what we might still reach and what we have already lost forever. Something is happening right now in the silence between these words. The distance between you and the nearest galaxy is growing, not because the galaxy is flying through space like a rocket, not because something is pushing it away, but because the space itself, the emptiness, the fabric, the stage on which everything exists, is quietly creating more of itself. Every second, new distance appears between things. The universe is not expanding into anything. It is simply becoming larger from within, like a breath that never stops growing. And this expansion is the edge, not a boundary you can touch, but a process that defines what is reachable and what is not. A moving threshold that determines which parts of the universe will remain connected to us, and which will drift away forever, carried by the silent tide of space itself. In 1929, Edwin Hubble stood at the eyepiece of the Hooker telescope and made a discovery that would rewrite humanity's understanding of existence. He had been measuring the light from distant galaxies, studying how their spectra shifted toward the red end of the spectrum. This redshift was a sign of motion, the Doppler effect applied to light. Just as the sound of a passing siren drops in pitch as it moves away, light from a receding object shifts toward longer, redder wavelengths. But Hubble noticed something extraordinary. Nearly every galaxy he observed was redshifted, and the farther away a galaxy was, the greater its redshift. This was not random. It was a precise mathematical relationship. Distance and recession velocity were linked by a constant ratio. If one galaxy was twice as far away as another, it was moving away twice as fast. 3 times the distance meant 3 times the speed. The pattern was undeniable. At first, this seemed to suggest Earth was at the center of a cosmic explosion, with everything fleeing from us in all directions. But this interpretation violated everything astronomers had learned about our place in the universe. We were not special. We were not central. So, what could explain this pattern? The answer came from the equations of general relativity, which had been sitting quietly in the literature waiting to be understood. Space itself could expand. Galaxies were not moving through space, they were being carried along by the expansion of space. It was as if the universe were a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. and from the perspective of any single raisin, all the others appear to be receding, with the farthest ones moving the fastest. No raisin is at the center. Every raisin sees the same pattern. This is the nature of cosmic expansion. It is uniform, democratic. Every point in space sees every other point moving away. There is no center to the expansion because the expansion is happening everywhere all at once. Scientists suggest that this expansion began with the Big Bang, though that name is misleading. The Big Bang was not an explosion in space. It was an explosion of space. Or perhaps more accurately, it was the moment when space began to exist and immediately started growing. In the first fractions of a second, this growth was unimaginably rapid, a period called cosmic inflation, where the universe doubled in size more than 60 times in less than a trillionth of a second. After inflation ended, the expansion continued, but at a much slower rate. For billions of years, gravity worked to slow this expansion. The mutual attraction of all the matter in the universe acted like a brake, pulling everything back together, fighting against the outward momentum. Physicists expected that eventually the expansion would slow enough to stop or even reverse, causing the universe to collapse back on itself in a big crunch. But in 1998, two teams of astronomers studying distant supernovae made a discovery that shocked the scientific world. The expansion of the universe was not slowing down. It was speeding up. Somehow, against all expectations, the universe was accelerating its expansion. Galaxies were pulling away from each other faster and faster, as if pushed by some invisible force. This mysterious force was given a name, dark energy. But the name is simply a placeholder for ignorance. We do not know what dark energy is. We do not know where it comes from or why it exists. We only know what it does. It pushes. It accelerates. It fills all of space with a kind of anti-gravitational pressure that grows stronger as the universe grows larger. Research shows that dark energy makes up roughly 68% of the total energy content of the universe. Dark matter. Another mysterious substance we cannot see or touch accounts for about 27%. And everything else, stars, planets, galaxies, gas, dust, light. Yumi. Everything we can touch and see makes up less than 5%. The universe is dominated by things we do not understand. But here's what we can measure, what we can quantify with extraordinary precision: the rate of expansion, the Hubble constant. This number tells us how fast space is growing. Currently, it sits at approximately 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance between two objects, the space between them is expanding at 70 kilometers per second. Let's pause and feel the weight of that. If you could somehow mark 2 points in empty space 1 megaparsec apart and return a second later, those 2 points would now be 70 kilometers farther apart. Not because they moved, but because new space appeared between them. Space is not a fixed stage. It is an active participant in the story of the universe. And this expansion creates consequences, strange, unsettling consequences. One of the most profound is that there is a distance beyond which objects are receding from us faster than the speed of light. Not because they are moving through space faster than light, nothing can do that, but because the space between us and them is expanding so quickly that the total rate of separation exceeds light speed. This distance, called the Hubble radius, is roughly 14 billion light-years away. Beyond this boundary, galaxies are receding faster than light. And because of this, light from those galaxies is not getting closer to us. It is, in fact, getting farther away. The photons are traveling toward us at the speed of light, but the space in front of them is expanding faster than they can cross it. They are running on a treadmill that accelerates faster than they can run. This is not a violation of relativity. Nothing is moving through space faster than light. But the combination of motion through space and the expansion of space itself can create effective separations that exceed light speed. And this creates a profound asymmetry in the universe. There are regions of space from which light will never reach us, no matter how long we wait. Imagine you are on a dock and a friend is rowing toward you from across a lake, but the dock is also moving away from your friend, carried by a current. If the current is slow, your friend will eventually reach you. But if the current is faster than your friend can row, they will never arrive. They will row forward, exhausting themselves, making real progress through the water. But the dock will always be receding, always out of reach. This is what happens to light from galaxies beyond the Hubble radius. But the situation is even stranger than this, because the Hubble radius is not fixed. As dark energy continues to drive the acceleration of the universe, the Hubble radius is actually shrinking in terms of the number of galaxies it contains. Galaxies that are currently within our observable universe are crossing the Hubble radius, entering a region where their light will never reach us again. They are not disappearing. They are simply becoming causally disconnected from us. We can still see them, but we are seeing them as they were in the past, frozen at the moment before they cross the boundary. We will never see what happens to them after that moment. Some scientists suggest this creates a kind of cosmic loneliness. The universe is becoming more isolated, more fragmented with different regions, losing the ability to communicate with each other. In the far future, trillions upon trillions of years from now, the only galaxies visible from Earth will be the ones gravitationally bound to us, our local group. Everything else will have slipped beyond the horizon, carried away by the relentless expansion. Now, here's a common misunderstanding. Many people imagine the expansion of the universe as something happening at the edges, as if space were growing outward from some central point. But this is not how it works. The expansion is happening everywhere at every point in space all at once. The distance between your hand and the wall is expanding. The distance between atoms in your body is expanding. But you do not notice this because the forces holding matter together, electromagnetic forces, nuclear forces, gravity on small scales, are far stronger than the expansion of space. They resist the expansion, keeping structures intact. Only on the largest scales where gravity is weak and distances are vast does the expansion dominate. Galaxies that are not gravitationally bound to each other drift apart. Galaxy clusters that are not part of larger superclusters separate. But within a galaxy, within a solar system, within an atom, the expansion is negligible, overpowered by stronger forces. This is why the Milky Way and Andromeda galaxies are on a collision course despite the expansion of the universe. They are close enough and gravitationally bound, strongly enough that their mutual attraction overwhelms the expansion. In about 4 billion years, they will merge, forming a single larger galaxy. And this new galaxy will remain intact, immune to the expansion, a small island of cohesion in a universe growing ever more diffuse. But step outside the gravitational influence of galaxy clusters into the vast voids of intergalactic space, and the expansion reigns supreme. These voids are growing. The distances between galaxy clusters are increasing. And because dark energy seems to be a property of space itself, a kind of energy density that remains constant, even as the universe expands, the total amount of dark energy in the universe is growing as new space is created. More space means more dark energy, which means faster acceleration, which means more space. It is a feedback loop with no known endpoint. Research shows that if this acceleration continues, the ultimate fate of the universe is something called the Big Freeze, or heat death. The universe will expand forever, becoming colder, darker, and more dilute. Stars will exhaust their fuel. Black holes will evaporate. Even protons might decay given enough time. And eventually, the universe will reach a state of maximum entropy where no energy gradients exist, where nothing can happen, where time itself becomes meaningless, because there is no change left to mark its passage. But this fate is so distant, so far in the future, that it feels almost abstract, trillions upon trillions of years away. For now, the universe is still young, still full of light and motion, still capable of surprise. And yet, even now, the expansion is writing stories of loss. Every moment, there are galaxies crossing the boundary, slipping beyond our reach. Their light is still traveling toward us, and we can still see them, but we are seeing their past. We will never know what happens to them in their future. We will never receive a signal from their present. They are leaving our story slowly, silently, without fanfare or farewell. Have you ever thought about what it means to lose something without it disappearing? The galaxies beyond the Hubble radius are still there, still real, still full of stars and worlds. But they are no longer part of our causal universe. They cannot affect us, and we cannot affect them. The connection has been severed not by destruction, but by distance, by the quiet, patient growth of space itself. This is the expansion's cruelest gift. It does not destroy. It simply separates. It turns neighborhoods into islands and islands into solitary points adrift in a sea that grows wider every second. And so, the edge is not a wall, it is a threshold, a moving line that determines what remains connected and what drifts into isolation. Space itself is the edge constantly redefining the limits of what we can touch, what we can see, what we can ever hope to know. But there is one more boundary even stranger than this, a horizon not of space but of fate, a line beyond which even the possibility of future interaction vanishes entirely. And once something crosses that line, it is gone from our universe in every meaningful sense, lost not to distance, but to the mathematics of acceleration and time. There is a line drawn across the universe that you cannot see, cannot touch, cannot cross. Not a line in space, but a line in possibility. On one side of this line are galaxies we might still reach if we left today and traveled at the speed of light for billions of years. On the other side are galaxies we have already lost, not because they have ceased to exist, but because the mathematics of expansion has sealed them away from us forever. Even if we could travel at light speed, even if we left this very moment and never stopped, we would never arrive. The destination would recede faster than we could approach. This boundary is called the cosmic event horizon, and it marks the difference between what is merely distant and what is absolutely permanently unreachable. Unlike the event horizon of a black hole, which traps light and matter behind a spherical boundary in space, the cosmic event horizon is a boundary in space-time itself. It divides the universe into regions that can still exchange information and regions that cannot. And once a galaxy crosses this horizon, it is gone from our future. We can still see it, but we are seeing its past frozen at the moment before it crossed. We will never know what happens to it after that instant. It becomes a memory preserved in light, but disconnected from the present. In 1916, Karl Schwarzschild, a German physicist serving on the Russian front during World War I, found the first exact solution to Einstein's field equations of general relativity. He was solving the equations for the gravitational field around a spherical mass, and he discovered something unexpected. If enough mass were compressed into a small enough volume, it would create a region of space-time so warped that not even light could escape. The boundary of this region became known as the Schwarzschild radius, or the event horizon of a black hole. At the time, this was considered a mathematical curiosity. Most physicists, including Einstein himself, believed that such extreme conditions could never occur in nature. But Schwarzschild's solution was correct. And decades later, astronomers would discover that black holes are not only real, but common. Millions of them exist in our galaxy, alone, remnants of massive stars that collapsed under their own gravity. The event horizon of a black hole is a point of no return. Once you cross it, you cannot come back. Not because there is a physical barrier, but because the geometry of space-time inside the horizon is such that all future paths lead inward toward the singularity at the center. Even if you traveled at the speed of light, you could not escape. The horizon is not a wall, it is a threshold in the structure of time itself. The cosmic event horizon works in a similar way, but in reverse. Instead of preventing things from escaping, it prevents things from arriving. It is a boundary beyond which the expansion of space is so rapid that even light cannot close the distance. A signal sent from beyond this horizon will travel toward us forever, but it will never reach us. The space in front of it expands faster than the signal can cross. Scientists suggest that this horizon exists approximately 16 billion light-years away, though the exact distance depends on the rate of cosmic acceleration and the properties of dark energy. Galaxies beyond this boundary are still visible to us because the light we are seeing was emitted billions of years ago before they crossed the horizon. But any light emitted from those galaxies now, at this moment, will never reach us. The connection has been severed, and here's the difficult part. This horizon is moving closer. As dark energy accelerates the expansion of the universe more and more, galaxies are crossing the cosmic event horizon every moment. They are slipping beyond our reach, not because they are speeding up, but because the finish line is moving away faster than they can approach. And once they cross, they are gone, permanently. Research shows that in the far future, billions of years from now, the only galaxies still visible from Earth will be the ones gravitationally bound to us, the Milky Way Andromeda, and a few dozen smaller galaxies in our local group. Everything else will have crossed the event horizon. The night sky will be almost empty. And future astronomers, if any exist, will look up and see a universe that appears static, small, and isolated. They will have no evidence of the billions of other galaxies that once filled the sky. No cosmic microwave background to study. No expansion to measure. They will live in a universe that has forgotten its own vastness. We are living in a unique moment in cosmic history, a brief window where the universe is still young enough to reveal its secrets, but old enough to be interesting. We can see the afterglow of the Big Bang. We can measure the expansion. We can trace the history of galaxies across billions of years. Future civilizations will not have these opportunities. They will inherit a universe that offers fewer and fewer clues about its origin and structure. But let's talk about what it means emotionally to lose something this way. When a star dies, it explodes or collapses, and we can witness the event. When a planet is destroyed, debris remains. But when a galaxy crosses the cosmic event horizon, nothing dramatic happens. It does not vanish in a flash. It does not send out a final signal. It simply continues existing somewhere beyond our reach, no longer part of our causal universe. The loss is silent, gradual, almost invisible, and yet it is absolute. There is no technology, no amount of time, no clever workaround that will let us retrieve what has been lost. Even if we could build a spacecraft that traveled at the speed of light, we could not reach those galaxies. The mathematics is unforgiving. The boundary is final. This creates a kind of cosmic grief, not for the destruction of something, but for the separation, for the knowledge that there are places out there full of stars and worlds that we will never be able to touch or explore. They exist, but they are no longer part of our story. Some physicists have compared this to the experience of losing someone to distance. Imagine a friend moving to another country, somewhere so remote that no letters, no phone calls, no messages can ever pass between you. They are still alive. They are still living their life, making choices, having experiences. But you will never know what happens to them. The connection is severed not by death, but by separation. This is what happens when a galaxy crosses the cosmic event horizon. One of the most unsettling aspects of the cosmic event horizon is that it is observer-dependent. Just like the observable universe, the event horizon is different for every observer. If you could somehow travel to a distant galaxy, your event horizon would move with you. Galaxies that were beyond your horizon from Earth might now be within reach. Others previously accessible would now be lost. This means the event horizon is not an objective feature of the universe. It is a relationship between you and the expansion of space, and every observer has their own version of it, unique to their location and motion. But there's a paradox hidden here. If every observer has their own event horizon, does that mean the universe is fragmented into countless isolated pockets, each one causally disconnected from the others? In a sense, yes. The universe is becoming more and more compartmentalized. Regions that can still communicate are growing smaller, Regions that cannot are growing larger. And eventually, on timescales so long they defy comprehension, the universe will consist of isolated islands of matter, each one alone in the dark with no way to know that anything else exists. This is sometimes called the Big Rip scenario. Though that name is misleading, the universe is not being torn apart violently. It is simply becoming more diffuse, more isolated, more lonely. The expansion is not destroying structure, it is creating distance so vast that structures can no longer interact. And here's something most people never consider. The cosmic event horizon applies not just to galaxies, but to information. Anything that happens beyond the horizon is unknowable to us. Events, discoveries, civilizations, if they exist beyond the boundary, they are inaccessible. There could be entire empires rising and falling, works of art being created, minds asking questions identical to ours, and we will never know. Not because the information is hidden, but because the structure of space-time prevents it from ever reaching us. Some scientists suggest this raises profound philosophical questions about the nature of existence. If something happens beyond the event horizon and we can never observe it or be affected by it, does it matter? Does it exist in any meaningful sense for us? This is not a question science can answer. It is a question about meaning, about connection, about what it means for something to be real. The cosmic event horizon also has implications for the ultimate fate of information in the universe. In physics, information is conserved. It cannot be created or destroyed, only transformed. But if information is constantly crossing the event horizon, leaving our observable universe forever, where does it go? Is it lost? Or does it still exist somewhere in some form, even though we can never access it? This is one of the deepest unsolved questions in cosmology, and it echoes a similar question that arises with black holes. When matter falls into a black hole, the information it carries seems to disappear behind the event horizon, lost forever. This violates the principle of information conservation, creating what physicists call the black hole information paradox. Some believe the information is somehow encoded on the surface of the event horizon, preserved in a form we don't yet understand. Others think it is genuinely lost, suggesting that our understanding of information conservation is incomplete. The cosmic event horizon presents a similar paradox. If galaxies and all the information they contain are crossing the horizon, slipping beyond our reach forever, is that information lost? Or is it preserved somewhere in some structure we cannot yet perceive? Research shows that these questions are at the frontier of theoretical physics, where general relativity and quantum mechanics intersect in ways we do not fully understand. The answers, if they exist, will require new theories, new mathematics, perhaps even new ways of thinking about reality itself. But for now, we can only watch as the horizon moves closer, claiming galaxy after galaxy, erasing connections that will never be restored. It is a slow goodbye stretched across billions of years, so gradual that no single generation will notice the loss. But it is happening. Every moment, the universe is becoming more isolated, more fragmented, more alone. Have you ever said goodbye to someone knowing you would never see them again? The cosmic event horizon is like that, but played out on the scale of galaxies. A permanent farewell not marked by words or rituals, but by the silent mathematics of expanding space. And yet, there is something almost beautiful in this. The fact that the universe has boundaries at all boundaries of knowledge, boundaries of connection, reminds us that we are finite beings in an unimaginably vast cosmos. We cannot know everything. We cannot reach everything. And perhaps that is okay. Perhaps the mystery is part of the meaning. But even the event horizon is not the final edge, because there are questions larger, still questions that ask, not just about what we can reach, but about whether our universe is alone. Whether the edges we have explored are boundaries of one universe among many, or the only universe there is. And the answers, if they exist, lie hidden in theories so strange they challenge the very idea of what it means for something to be real. What if the universe, every galaxy, every star, every atom that has ever existed, is just one bubble in an infinite foam? What if beyond the edge we've been searching for, there is not emptiness, not an ending, but another universe entirely? A place where the laws of physics are different, where light moves at a different speed, where gravity pulls with a different strength, where even the fundamental constants that make matter possible have values nothing like our own. And what if there are not just two universes, but countless trillions, each one, a separate bubble expanding in its own direction, forever isolated from all the others? This is the multiverse, not science fiction, but a serious possibility that emerges naturally from the mathematics of cosmic inflation, a concept so vast it makes our observable universe feel small. The idea of multiple universes is not new. Philosophers and theologians have speculated about parallel worlds for centuries. But in modern physics, the multiverse is not a matter of imagination. It is a prediction, an almost unavoidable consequence of the theories we use to explain the early universe. And if it is real, then the edge of our universe is not the edge of everything. It is simply the edge of our bubble, one boundary among infinite boundaries, one horizon among infinite horizons. In the early 1980s, a young physicist named Alan Guth was struggling with a problem. The universe, according to observations, was extraordinarily uniform. No matter which direction astronomers looked, the cosmic microwave background had almost exactly the same temperature. This uniformity was puzzling. How could regions of space that had never been in contact with each other, regions so far apart that light could not have traveled between them, since the Big Bang, end up at the same temperature? It was like finding two isolated rooms, each heated by a separate furnace, and discovering they were both exactly 72 degrees. How could they coordinate? Guth proposed a solution. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. Space doubled in size, then doubled again, then again more than 60 times in less than a trillionth of a second. This rapid expansion took a tiny causally connected region, a patch of space where all parts were in thermal equilibrium, and stretched it to a size much larger than the observable universe today. This solved the uniformity problem. The universe looks the same in all directions, because it all started from the same small, smooth patch. But Guth's colleague Andre Linde noticed something strange about the mathematics of inflation. Once inflation starts, it is very difficult to stop. In most regions of space, inflation continues forever. Only in rare pockets does it slow down and stop allowing matter and energy to condense into galaxies and stars. These pockets become universes, bubbles of stable space embedded in a background of eternally inflating space. And each bubble is causally disconnected from all the others. They cannot communicate. They cannot interact. They are, for all practical purposes, separate universes. This is called eternal inflation, and it suggests that our universe is not unique. It is one bubble among an infinite number of bubbles, each one born from a quantum fluctuation in the inflating background, each one expanding and cooling and forming its own structures. Some of these bubbles might be similar to ours, others might be radically different. And because inflation is eternal, new bubbles are constantly forming. The multiverse is not a static collection. It is a continuously growing foam with new universes appearing all the time. Scientists suggest that if eternal inflation is correct, then the multiverse is not just large, it is infinite. There is no edge to the multiverse because the inflating background extends forever in all directions, and within it, bubbles continue to nucleate without end. This means that not only are there other universes, but there are infinitely many of them. And in an infinite multiverse, every possible configuration of matter and energy that can exist does exist, somewhere. This idea has profound implications. It means there are other universes where the laws of physics are slightly different, where the strength of gravity is a bit stronger, causing stars to burn faster and die younger, where the charge of the electron is different, making chemistry impossible, where the cosmological constant is so large that galaxies never form at all. And it means there are also universes almost identical to ours. Universes where Earth exists, where humans evolved, where you are sitting right now listening to these words. But in one of those universes, you chose to stand instead of sit. In another, you pause this video. In another, still you never found it at all. The infinite multiverse hypothesis is both exhilarating and unsettling. It suggests that nothing is unique, that every choice, every event, every possibility is realized somewhere. And yet none of those other universes can ever affect us. They are beyond our cosmic horizon, separated not just by distance, but by the structure of space-time itself. But here's where the idea becomes even stranger. Research shows that in some models of the multiverse, the different bubbles have different dimensionalities. Our universe has 3 dimensions of space and 1 of time. But other bubbles might have 4 spatial dimensions, or 2, or 7. The number of dimensions is determined by how the fundamental fields settle into their lowest energy state during the formation of each bubble. And if the number of dimensions is different, the laws of physics are completely different. Gravity weakens faster in higher dimensions. Atoms cannot form in the same way. Planet stars life as we know it, none of it would be possible. This raises a troubling question. If most bubbles in the multiverse are inhospitable to life, why do we find ourselves in one of the rare bubbles where the constants are fine-tuned for complexity? One answer is the anthropic principle. We observe this universe because we could not exist in any other. It's a selection effect. Out of infinite bubbles, only a tiny fraction have the right conditions for life. And we necessarily find ourselves in one of those because we could not have evolved anywhere else. But this explanation feels unsatisfying to many physicists. It shifts the question from, why is the universe this way, to, why are we able to ask the question at all? And it gives up on finding a deeper reason for the values of the fundamental constants. They are what they are in our bubble, simply because if they were different, we would not be here to wonder about them. Now, let's talk about the edges. If our universe is a bubble, what is the edge of the bubble made of? Is it a physical boundary? A wall we could touch if we traveled far enough? The answer is no. The edge of a bubble universe is not a place in space. It is a transition in the state of the inflating field. Inside the bubble, the field has settled into a stable configuration, allowing matter and energy to exist. Outside the bubble, the field is still inflating, doubling in size every fraction of a second, too turbulent for particles to form. If you could somehow approach the edge, and you cannot, because the bubble is expanding faster than you could ever travel, you would not see a wall. You would not see anything, because space itself, on the other side, is expanding so rapidly that light cannot propagate. It would be like trying to swim against a current moving faster than the speed of light. You would make no progress. You would never reach the boundary. And even if you did, there would be nothing on the other side for you to interact with. Just eternally inflating space, smooth and empty, generating new bubbles elsewhere. This means the edges of bubble universes are not like the edges of objects. They are more like phase transitions, like the boundary between water and steam. On one side, molecules are slow and bonded together. On the other, they are fast and dispersed. The transition is continuous, but the properties on either side are completely different. And here's the most disorienting part. In eternal inflation, the distance between bubbles is not fixed. The inflating background is expanding, so bubbles that form near each other are carried apart at exponential speeds. 2 bubbles might be created only a microsecond apart in regions of space that are initially close together. But within moments, the inflating space between them has stretched to such an extent that they can never interact. They are separated by an unbridgeable gulf of eternally inflating space. Some scientists suggest that this makes bubble universes fundamentally unobservable. If we cannot see them, cannot reach them, cannot receive signals from them, do they exist in any meaningful sense? Or are they simply mathematical artifacts of our theories, things that appear in equations but have no connection to physical reality? This question divides the physics community. Some argue that the multiverse is a natural consequence of inflation, and we should take it seriously, even if we cannot observe it directly. Others insist that science must be based on observation and testability, and if the multiverse is forever beyond our reach, it belongs to philosophy, not physics. But there is one piece of evidence that might support the multiverse, or at least make it testable. If our bubble universe collided with another bubble in the distant past, it would leave a mark, a pattern in the cosmic microwave background, a disc-shaped region with slightly different properties than the surrounding sky. Astronomers have searched for such anomalies and found a few candidates regions where the temperature fluctuations seem unusually aligned, where the statistics deviate slightly from randomness. But none of these signals are strong enough to be conclusive. They could be coincidences, or artifacts of the data, or evidence of something else entirely. For now, the multiverse remains theoretical, a prediction of our best models, but not yet a confirmed feature of reality. And perhaps it never will be. Perhaps there are truths about the cosmos that lie forever beyond the reach of observation, truths we can infer but never verify. Have you ever wondered what it would feel like to live in a different universe, a place where the sky is a different color, where stars burn differently, where the fundamental forces of nature follow unfamiliar rules? In some bubble universes, you could not exist. In others, life might take forms we cannot imagine. And in just a few conditions might be similar enough to ours that beings like us could evolve, could look up at their sky, could ask the same questions we are asking now. But we will never meet them. The boundaries are too vast, the separation too absolute. And so, the multiverse, if it exists, is a place of infinite loneliness, infinite worlds, each one isolated, each one, believing it might be the only one each one's searching for. An edge that leads only to more edges, more bubbles, more unknowable distances. And perhaps this is the deepest lesson of the multiverse, that edges do not always mean endings. Sometimes they mean beginnings. Sometimes they mean transitions. And sometimes they mean that the thing you thought was everything is just one small part of something unimaginably larger. But even the multiverse, vast as it is, has an edge of a different kind, not a boundary in space, but a boundary in time. Because no matter how many universes exist, no matter how many bubbles form and expand, they all share one unavoidable fate. A slow descent into silence, into cold, into the final edge, where even possibility itself runs out. And that edge is waiting patient and inevitable at the end of everything. Imagine a universe where every star has burned out, where every black hole has evaporated into nothingness, where every last photon has been stretched by expansion until its wavelength is longer than the observable universe itself. A cosmos so cold, so dark, so perfectly uniform that nothing can ever happen again. No energy flows, no structures form, no thoughts arise. Time itself becomes meaningless because there is no change left to mark its passage. This is not the edge of space. It is the edge of time, the final boundary, the moment when the universe reaches maximum entropy and possibility itself comes to an end. Physicists call it heat death, but the name is misleading. It is not hot. It is the coldest, quietest, most still thing imaginable. The universe, having spent all its energy, simply stops. This is the ultimate fate predicted by the second law of thermodynamics. Not an explosion, not a collapse, just a slow, patient descent into equilibrium. And unlike the other edges we have explored, edges of visibility, edges of connection, edges between universes, this edge is unavoidable. It waits at the end of every timeline, no matter how the universe expands, no matter what dark energy does, no matter how many galaxies slip beyond our horizon. Entropy always increases, and eventually it will increase until there is nothing left to organize, nothing left to change, nothing left to be. In the mid-19th century, a German physicist named Rudolf Clausius formulated the second law of thermodynamics. It states simply that in any closed system entropy, a measure of disorder tends to increase over time. Heat flows from hot objects to cold objects, never the reverse. Energy spreads out, becoming more evenly distributed. And once everything reaches the same temperature, no further work can be done. The system reaches equilibrium. And equilibrium in thermodynamics is death. Clausius applied this principle to the universe as a whole. If the universe is a closed system and entropy always increases, then eventually the universe will reach a state of maximum entropy. All energy will be evenly distributed, all temperatures will be the same, and no energy gradients will exist to drive processes to power stars, to sustain life, to allow anything to happen. He called this the heat death of the universe, and he predicted it was inevitable. At the time, this idea was deeply unsettling. It suggested that the universe had a finite lifespan, not because it would be destroyed, but because it would simply run out of usable energy, like a clock winding down, eventually coming to a stop. And once it stopped, it could never start again. There would be no reset, no new beginning, just eternal stillness. For decades, scientists debated whether the second law of thermodynamics truly applied to the universe as a whole. Some argued that the universe might not be a closed system. That energy could somehow be replenished from outside, but as our understanding of cosmology deepened, it became clear that there is no outside. The universe is everything. And if the second law holds, and all evidence suggests it does, then heat death is not just a possibility. It is the only possible end. Research shows that the timeline for heat death is almost incomprehensibly long. We are not talking about billions of years or even trillions. We are talking about timescales that stretch beyond human comprehension. The current age of the universe, 13.8 billion years, is barely the first tick of a cosmic clock that will run for googles of years, 10 to the power of 100 a number, so large it exceeds the number of atoms in the observable universe. Let's walk through the stages slowly so you can feel the weight of deep time. Right now, the universe is in what cosmologists call the stelliferous era, the age of stars. Galaxies shine. Stars burn hydrogen into helium, releasing light and heat. Planets orbit. Life exists, at least here on Earth, and possibly elsewhere. This is the universe at its most vibrant, its most dynamic. But this era will not last forever. In about 1 trillion years, the last stars will begin to die. Star formation requires gas hydrogen clouds that collapse under gravity, igniting fusion in their cores. But over time, this gas is used up, converted into heavier elements, or locked away in dead stars. Eventually, there will be no gas left. No new stars will form. The galaxies will grow dark, populated only by stellar remnants, white dwarfs, neutron stars, black holes, and the occasional dim brown dwarf, too small to ignite fusion, glowing faintly with residual heat. This marks the beginning of the degenerate era, a universe lit not by fusion, but by the slow cooling of dead objects. White dwarfs will radiate their stored heat into space, growing colder and colder over trillions of years, eventually becoming black dwarfs, cold, dark spheres of carbon and oxygen invisible against the void. Even these will not last forever. Protons. The building blocks of atomic nuclei are thought to be unstable over extremely long timescales. Research suggests they may decay into lighter particles after about 10 to the power of 34 years. If this is true, then even black dwarfs will eventually disintegrate, dissolving into radiation and exotic particles. By 10 to the power of 40 years, the only large structures remaining will be black holes. Everything else, stars, planets, galaxies, will have decayed or evaporated. The universe will enter the black hole era, and black holes, despite their reputation for permanence, are also temporary. In 1974, Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint, far too weak to detect from any black hole that exists today. But over unimaginable timescales, it causes black holes to lose mass. Slowly, particle by particle, they evaporate. The time it takes for a black hole to evaporate depends on its mass. A black hole with the mass of the Sun would take about 10 to the power of 67 years to completely evaporate. Supermassive black holes, like the ones at the centers of galaxies, would take even longer 10 to the power of 100 years or more. But eventually they all evaporate. And when the last black hole finally disappears in a faint burst of radiation, the universe will enter its final era, the dark era. In the dark era, nothing remains but a thin soup of particles, photons, neutrinos, electrons, positrons, spread so thinly across space that they almost never interact. The temperature of the universe will be unimaginably close to absolute zero. Space will continue expanding, driven by dark energy, stretching the distances between particles until they are separated by light years, then millions of light years, then billions. The universe will be dark, cold, empty, and silent, and it will remain this way forever. Scientists suggest that in this final state, entropy has reached its maximum. Every energy gradient has been erased, every temperature difference has been equalized, and with no gradients, no differences, no imbalances, nothing can happen. No processes can occur. No structures can form. Time in a functional sense stops. Not because time itself ceases to exist, but because there is no change left to measure. The universe becomes a static, frozen tableau, unchanging for eternity. This is heat death, not a fiery end, but a cold one. Not a collapse, but a dissipation. The universe does not die in a moment. It fades slowly across timescales so vast they dwarf the entire history of stars and galaxies. And when it is finally over, there is nothing left but the memory of what once was encoded in the faint, scattered photons that no longer have the energy to interact with anything. But here's a question that haunts physicists. If the universe reaches heat death, if entropy maximizes and nothing can ever happen again, is that truly the end? Or could there be some process, some quantum fluctuation, some mechanism we don't yet understand that allows the universe to restart? Could heat death be not an ending, but a transition to something else? One idea proposed by physicist Roger Penrose is called conformal cyclic cosmology. Penrose suggests that after the universe reaches maximum entropy, after all matter has decayed, and only massless particles remain, the universe loses all sense of scale. Without matter to define size, without energy gradients to define structure, space becomes smooth and uniform. And in this smooth, uniform state, the geometry of space-time can transform. The infinite future of one universe becomes the Big Bang of the next. Heat death and rebirth are the same event seen from different perspectives. This idea is speculative, poetic, and difficult to test, but it offers a kind of hope. The possibility that endings are not truly final, that the universe might renew itself, cycling through phases of expansion, heat death, and rebirth over and over eternally. But even if this is true, each cycle is isolated. Information from one cycle does not pass into the next. Each new universe begins from scratch with no memory of what came before. Other physicists propose different scenarios. Some believe that quantum fluctuations in the vacuum could spontaneously create new universes even in the dark era. These would be tiny, short-lived bubbles of space-time existing for fractions of a second before collapsing back into the void. And very rarely, perhaps, once in 10 to the power of 10 to the power of 100 years, a fluctuation might be large enough to create a new Big Bang, a new inflating universe, a new beginning. But the odds are so astronomically small that even the word rare feels inadequate. And then there is the possibility that we are simply wrong, that our understanding of thermodynamics or quantum mechanics or general relativity is incomplete, that there are processes or forces we have not yet discovered that could prevent heat death or reverse it or transform it into something we cannot currently imagine. Physics is not finished, and every generation of scientists has encountered phenomena that previous generations could not have predicted. But based on what we know now, heat death is the most likely fate. And it is not a fate that can be avoided by traveling somewhere else or hiding in a distant galaxy or escaping to another universe, because heat death is not a localized event. It is a universal condition, a state that the cosmos as a whole approaches asymptotically, like a curve approaching a line, but never quite touching. Except in this case, the curve does touch, eventually. Have you ever wondered what it would be like to be the last thing in the universe? The last star burning alone in an ocean of darkness with no companions, no witnesses, no one to remember it when it finally goes out. Or perhaps the last black hole evaporating slowly over eons, radiating faint particles into a void that no longer cares. There is something almost tragic in the idea, not because the universe is destroyed, but because it is forgotten, because all the complexity, all the beauty, all the meaning that ever existed dissolves into a featureless uniformity. And yet, perhaps there is peace in this too, because heat death is not violent. It is the gentlest possible ending, no cataclysm, no suffering, just a slow, patient return to simplicity. The universe, having tried everything, having formed every structure that could form, having explored every possibility that could exist, finally rests. And in that rest, there is a kind of completion, a sense that the story has been told fully and completely with nothing left unsaid. But even as we contemplate this distant ending, we are still here now, in the stelliferous era, surrounded by light and motion and possibility. The universe is young. The stars are bright, and we have been given the extraordinary gift of existing during the only time when the cosmos can be understood, when evidence of the Big Bang is still visible, when galaxies still shine, when the questions we ask can still be answered. Perhaps that is the real edge, not the heat death waiting in the unimaginable future, but the present moment. The boundary between what we can know and what we cannot. The thin sliver of time where the universe is neither too young to have structure nor too old to remember its origins. We stand at this edge now, looking backward at the light of creation and forward at the darkness of eternity. And for this brief, precious moment, we can see both. But there is one more thing to consider before this journey ends. One final question that ties all the edges together, the horizon of light, the boundary of space, the limits of time. Because perhaps the greatest edge is not out there in the cosmos, but here within us. The edge between knowing and not knowing, between wonder and understanding, between the vastness of the universe and the smallness of a single mind trying to comprehend it all. There is a photograph taken in 1990 by the Voyager 1 spacecraft. It was already 6 billion kilometers from Earth, speeding toward the outer reaches of the solar system, when mission scientists commanded it to turn around one last time and look back. The camera captured Earth as a single pixel, a pale blue dot suspended in a beam of scattered sunlight, barely visible against the vastness of space. In that image, every human who has ever lived, every war fought, every monument built, every poem written, every moment of love and loss, all of it contained in a speck of light, smaller than a grain of sand held at arm's length. Carl Sagan, reflecting on this image, wrote that it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Because from out there, from the perspective of cosmic distances, our world is not the center of anything. It is a mote of dust floating in a sunbeam. And yet, it is where we stand. It is the edge of everything we can touch, everything we can change, everything that truly matters. We have traveled far in this journey. We began at the horizon of everything, at the question of where the universe ends. We passed through the oldest light, the cosmic microwave background, and learned that some edges are made not of walls, but of transparency and time. We explored the observable universe, a sphere centered on us, not because we are special, but because every observer stands at the center of their own horizon. We ventured beyond what we can see into regions that exist, but remain forever unreachable, separated by the expansion of space itself. We cross the cosmic event horizon, where galaxies slip away from our story, lost not to destruction, but to distance. We imagine the multiverse, where our universe might be one bubble among infinite bubbles, each one isolated, each one containing its own edges. And we looked ahead to the heat death, the final boundary where time itself loses meaning, and the universe settles into eternal stillness. But through all of these edges, one truth has persisted. The edges are not out there, they are also here. They are the limits of what we can know, what we can reach, what we can comprehend. And perhaps most importantly, they are reminders of where we stand in the vast and different cosmos, not at the center, not at the edge, but somewhere in between, looking outward with curiosity, looking inward with wonder, trying to make sense of our place in a story that began long before us and will continue long after. Research shows that humans have always been drawn to edges. We climbed mountains to see what lay beyond. We sailed across oceans toward unknown shores. We built telescopes and spacecraft to extend our vision into the farthest reaches of space. This drive to explore, to understand, to push against the boundaries of the known, it is one of the defining characteristics of our species. And it has led us to discoveries that would have seemed like magic to our ancestors. We have mapped the genome. We have photographed black holes. We have sent machines to other planets and listened for signals from distant stars. We have learned that the universe is 13.8 billion years old, that it is expanding, that it contains hundreds of billions of galaxies, each one filled with hundreds of billions of stars. And yet, for all we have learned, the universe remains mostly mysterious. We do not know what dark matter is. We do not know what dark energy is. We do not know if the multiverse is real. We do not know if there is life elsewhere in the cosmos. We do not know how consciousness arises, or why the laws of physics have the values they do, or what happened in the very first instant of the Big Bang. We stand at the edge of knowledge, peering into the unknown, and the unknown is still vast. But perhaps this is not a failure. Perhaps this is the point, because the edges we have explored tonight are not barriers. They are invitations, invitations to wonder, to question, to imagine. The cosmic microwave background does not say you cannot look further. It says, here is the oldest light you will ever see. What can you learn from it? The event horizon does not say you cannot reach those galaxies. It says, these galaxies are slipping away. What does that teach you about the nature of space and time? The heat death does not say everything is meaningless. It says, you have been given a finite amount of time in a universe that will not last forever. What will you do with it? Some scientists suggest that the purpose of science is not to answer every question, but to ask better questions, to replace simple mysteries with deeper mysteries, to trade ignorance for understanding, and then discover that understanding reveals even greater layers of complexity. This is not frustrating, it is exhilarating, because it means the journey never ends. There is always another edge to explore, another horizon, to cross another boundary to contemplate. And consider this. Right now in this moment, you are standing at the most privileged point in cosmic history. The universe is old enough to have formed stars, planets, and life. It is young enough that the evidence of its origins is still visible. The cosmic microwave background still glows. Galaxies still shine. The expansion can still be measured. In trillions of years, these gifts will be gone. Future beings, if any exist, will inherit a darker, emptier cosmos, one that offers fewer clues about where it came from or where it is going. But you are here now. You have access to the story. You can see the beginning and imagine the end. You can trace the history of the universe from the Big Bang to the heat death, from the first light to the final darkness. You live in the golden age of cosmology, and you probably did not even realize it until this moment. Do you ever stop to think about how extraordinary it is that you can understand these things at all? That a collection of atoms arranged in a particular pattern inside your skull can contemplate the fate of the entire universe? That evolution acting blindly over billions of years produced a species capable of asking where the edge of everything is. The universe spent 13.8 billion years becoming complex enough to ask questions about itself. And you are part of that process. You are the universe thinking about the universe. You are stardust contemplating stardust. And that alone is worth marveling at. There is a concept in philosophy called the overview effect. It describes the cognitive shift that astronauts experience when they see Earth from space for the first time. From orbit, national borders disappear, conflicts seem trivial, the fragility and interconnectedness of life become undeniable. Many astronauts report that seeing Earth from this perspective fundamentally changed how they understood their place in the world. They felt smaller, but also more connected, more aware of their responsibility to protect the only home we have. Perhaps contemplating the edge of the universe offers a similar shift. When you realize how vast the cosmos is, how many galaxies exist beyond our reach, how many edges there are that we will never cross, it puts everything into perspective. Your problems, your worries, your achievements, your failures, they are all happening on a tiny world in a tiny corner of one galaxy among hundreds of billions. And yet, they matter. Because they matter to you. Because you are here now experiencing them. Because the universe does not have meaning on its own. Meaning is something we create, something we give to the world through our choices, our connections, our willingness to care about something other than ourselves. Carl Sagan also said that we are a way for the cosmos to know itself. And this is true. But it is also incomplete, because we are not just passive observers. We are participants. We are builders and destroyers, creators and consumers. We shape the world around us for better or worse. And in doing so, we determine what kind of story our species will tell. Will we be remembered as the beings who reached beyond our small world, who sought to understand the universe, who cared for each other, and for the fragile planet that gave us life? Or will we be a footnote, a brief flicker of complexity in the long, slow march toward entropy? The edge of the universe is not a place you can visit, but the edge of human potential is still unwritten. We do not yet know how far we can go, what we can discover, what we can become. And perhaps that is the most important edge of all, the boundary between what we have done and what we might still do, between who we are and who we could be. So, as we come to the end of this journey, let's remember something simple. The universe is vast, ancient, mysterious, and beautiful. It does not care about us. It does not know we exist. And yet, we exist anyway. We look up at the night sky and see not just light, but stories. We build telescopes and write equations and send spacecraft into the void. We ask questions that have no easy answers. We seek edges that recede as we approach. And we do all of this not because we expect the universe to reward us, but because it is in our nature to wonder. The edge of the universe is wherever we stop looking. And as long as we keep looking, keep asking, keep pushing against the limits of what we know, the edge will always be just a little bit farther than we thought. Just out of reach, just beyond the horizon, waiting patiently for us to take one more step. Thank you for drifting with me through the edges of everything, for spending this quiet night exploring the boundaries of space-time, knowledge, and possibility, for wondering alongside me what it all means. The universe is still here, still expanding, still full of mysteries. And so are you, still curious, still searching. Still standing at your own edge, looking outward, looking inward, trying to make sense of it all. If these gentle journeys through the cosmos bring you peace, if they help you rest a little easier beneath the weight of infinite questions, then I hope you will join me again. There are more stories to tell, more edges to explore, more quiet nights where science and wonder meet in the space between stars. Sleep well. Dream at the edge of everything. And when you wake, remember that you are part of this vast, beautiful, unfinished story. You are not just looking at the universe. You are the universe looking at itself, and that is more than enough. Good night,